For centuries, men have pondered the mysteries of their world and the heavens above. Often their questions have been quite limited.
Why does rain fall?
And the answers have been equally specific.
Because heat from the sun turns water to vapor, which rises, cools, and returns to earth as rain.
Often the questions have been more far-reaching.
What is the smallest particle of matter?
And the answers have had almost unending implications.
The atom is the tiniest known unit of matter.
At times, the mere struggle to survive has left man with energy to do little more than accept the workings of nature. But at other times, man has had enough leisure to pursue a desire to know. Sometimes the resulting discoveries have revolutionized man's thinking about himself, his world, and the universe, and have had consequences far into the future. The years between 1540 and 1700 was such a period. A number of brilliant and inquisitive men laid the foundations of modern science. To appreciate their achievement, we must understand some of the concerns and assumptions of the science that they displaced. With the collapse of the Roman Empire, Europeans were plunged into centuries of barbarism. Survival became one of the chief concerns of the people. By the 12th century, life was more secure, with more time for leisure and for study. Contact increased with the outside world, with societies that owed much of their cultural superiority to the preservation of Greek science and learning. Among these were the Byzantine Empire and Moorish Spain. In the philosopher Averroes, Muslim Spain had one of the medieval world's finest scholars, a man who dedicated his life to furthering the thought of the ancient Greek philosopher Aristotle. The teaching of Aristotle was the supreme truth because his mind, said Averroes, was the final expression of the human mind. Aristotle's writings on logic formed a systematization of learning, more complete than any other ever attempted in the ancient world or the medieval one. Western Europeans found, for the first time, the tools essential to orderly thinking. They learned to state a proposition and to reason step by step to a logical conclusion. Even God was not immune to having his nature probed through the use of logic. At the University of Paris, Aristotle's works were used for a time and then banned. Church leaders were outraged by the idea that mere mortals might penetrate the nature and designs of God. In school after school, logic became the principal subject of the curriculum, required for the study of law, medicine, and theology. Within a little more than a century, all of Aristotle's works, plus numerous commentaries, were available in translation and even found in the Pope's own library. Many scholars were trying to marry Greek learning to Christian doctrine in a kind of curriculum guide called a Summa. The supreme achievement in binding together the Judeo-Christian and Greek traditions was the work of St. Thomas Aquinas. Aquinas' philosophical system, though Christian in spirit, was Aristotelian in its assumption that everything in the universe had a natural place and function, from a grain of sand and the mightiest tree to man and the heavens above. Medieval society was itself hierarchical. At the top were pope and emperor. Then came bishop and king, abbot and prince, priests and nobles, townspeople and serfs. Aquinas also adopted Aristotle's belief that the highest science, the highest philosophy, was the study of first causes, of that which caused all things in the universe. To Aquinas, this belief in first causes was akin to his own belief in the God of the Old and the New Testaments. Aristotle had taught that only by directly observing nature could man begin to understand first causes. But Aquinas was a theologian, not a scientist. He had no real interest in observing the natural world. To Aristotle, the form of every living thing was determined from before birth, and gave a thing its identity. An animal's nature and form were inseparable. Growth itself was nothing more than the unfolding of this nature and form. Birth and growth, death and decay, the constant ebb and flow of identifiable forms of life, formed the foundation of Aristotle's view of the world. From observations, Aristotle came to believe that everything in the world had a nature and a purpose. Rain fell to nourish crops. Sandals existed to cover and protect feet. Aristotle condemned an idea first advanced by an earlier Greek named Democritus, that all things consisted of a single element of randomly interacting atoms. To Aristotle, all matter was made up of 4 purposeful elements. Earth and water he classified as heavy, and fire and air as weightless. Bound up with this theory of the elements was his theory of the 4 primary qualities, a pair of which was to be found in each element. Fire was hot and dry. Air, hot and moist. Water, moist and cold. And earth, dry and cold. Everything had one or more of the qualities. Closely tied to the theories of the elements and the qualities was the theory of change. Water, Aristotle observed, was changed by the sun's heat into air. Since air was weightless, according to Aristotle, it rose, searching for its natural resting place. Then, high above the earth, the air was cooled and changed back to water. And water, being a heavy element, returned to earth as rain, in search of its natural resting place. Aristotle concluded that one element could be transformed into another through a substitution of qualities. If an element did not always behave according to its nature, as in the case of fire, lightning, striking downward, it was, Aristotle explained, because the elements, as woven together on earth, were out of their natural resting places and thus unstable. If the elements ever succeeded in coming to rest, which was their natural condition, all change would cease and the world would become absolutely motionless. Aristotle observed 3 other kinds of change. The first can be seen in the example of a man who is happy one day and sad the next, but who on both days is the same man. A second kind of change can be seen in the example of a goat that gives birth to a pair of kids and months afterward to another pair while continuing to exist herself. The last kind of change identified by Aristotle was that in location. We call it motion and think of it as a process. But to Aristotle it was a sequence of changes from one point to another, each occurring in a straight line, since this was the only direction possible for earthly motion. Since all earthly motion was thought to be unnatural, it was necessary in Aristotelian science to identify a mover, the agent that brought about the change in location. The agent made the change by exerting an excessive effort over the natural resistance of whatever was being moved. As long, said Aristotle, as the effort and resistance remained constant, the speed at which the thing was being moved would remain constant. There was no attempt to account for acceleration. Aristotle also observed falling bodies. He learned that stones of equal weight, dropped into fluids of unequal density, fall at different rates of speed, because they encounter different amounts of resistance. Aristotle assumed that what was true of stones falling in fluids should also be true of stones falling in air. A large stone, he said, would exert more effort than a small one, and thus fall at a greater rate of speed. If there were no resistance, that is, if there were a vacuum, the rate of speed would be infinite. Since Aristotle knew this to be impossible, he asserted that a vacuum could not be created or found in nature. If the earth was a place of constant change, the heavens were eternal and unchanging perfection. This heavenly or lunar world, said Aristotle, revolved around the earth, which was the center of the universe. Since the lunar world was composed of a fifth element, a pure, fiery substance called quintessence, it provided the earth with a never-failing source of light. In addition, the circular and perpetual motion of this element accounted for the routine reappearance of the sun, the moon, and the planets. During the 2nd century, it became clear that Aristotle's explanation was too simple, that the planets did not move in unchanging circles. To the great astronomer of Alexandria, Claudius Ptolemy, the planets seemed to move for a time in one direction and then backward. To account for this peculiarity, Ptolemy devised a complicated system in which each of the planets was treated separately. It became the task of other astronomers to make minor modifications in this system in order to keep it and the calendar accurate with the seasons. This meant the addition of new complications. Finally, in Aristotle's universe there was man, situated between Earth and the lunar world. Only man possessed an intellectual soul, a nature capable of detaching itself from the mechanics of the body and reflecting on the whole of creation. Such an idea was easily accepted 1,500 years later by Aquinas and other Christian thinkers, since it was a principle of Christian doctrine that man, made in the image of God, was the center of creation. This was the state of Western science on the eve of the scientific revolution. Science itself was but one level in a structure of thought crowned by theology. Philosophically, the structure was dominated by Aristotle. A bright new star, brighter than anything in the sky except the sun, the moon, and Venus. So bright that it could be seen during the day. Throughout most of 1573, the star remained, not disappearing until early 1574. How could there be a new star in the heavens? Did not the Church teach that on the seventh day God ceased the work of creation and afterward created nothing more? And did not Aristotle's science teach that the heavens were perfect, eternal, and unchanging? Men reasoned that perhaps what they had seen was not a star at all, but a ball of fire that had risen from the earth and become trapped on the earthly side of the heavens. 3 years later, the appearance of a new comet made acceptance of the old explanations more difficult. What was needed was a new theory of the heavens. Unknown to most people, a new theory had already been advanced. In 1543, Nicholas Copernicus, an obscure Polish monk, published a painstaking mathematical analysis of Ptolemy's astronomical observations, still the world's most accurate after 1,300 years. Copernicus merely wanted to free astronomy from Ptolemy's complexities. Copernicus accepted Aristotle's views on the circular motion of the heavens and on the movement of earthly bodies. Copernicus wondered whether many problems in astronomy might disappear if one assumed that the sun, and not the earth, was the center of the universe. Copernicus also wondered whether the sequence of day and night could be caused by the daily rotation of the earth on its axis, rather than by the orbiting of the sun around the earth. Years later, people look back on these two theories as the start of the scientific revolution. Gradually, a new science was to arise. It was to be based on observation, experimentation, mathematical analysis, and a new kind of conceptual thinking. Most people resisted every step in the direction of this science. The fiercest resistance came from the political and religious authorities. To them, the new science was blasphemy, for it threatened the very foundations of their authority. Martin Luther, with all his unorthodox opinions, was typical of this kind of conservatism. Of Copernicus, he said, "The fool would overturn all astronomy." But in the Holy Scriptures we read that Joshua ordered the sun to stand still, not the earth. Common sense, as well as authority, was against the new science. As long as men lacked instruments of observation and measurement, they were forced to rely on their senses and their reason. Not until the end of the 1500s did the essential instruments of the new science begin to appear. And it was another half-century or more before all of them were available. Meanwhile, men of action were gathering masses of new knowledge about the world. Portuguese and Spanish sea captains were discovering new routes to India and establishing empires in America as well as in Africa and Asia. Expert map makers were producing more accurate sailing charts. Italian engineers were applying new scientific principles to the improvement of canals, locks, and harbors. German mine owners were utilizing new mining techniques. Painters were experimenting with light, color, and perspective. Architects were studying the laws of proportion, and musicians the mathematics of harmony. The development of printing enabled the growing number of literate people to read of these discoveries, and of the most recent uncoverings of ancient learning. Among these were the writings of a supposedly ancient Egyptian named Hermes Trismegistus. By the time it was learned that these writings were forged, they had given new life to a tradition of thought stretching back more than 2,000 years to the ancient Greek mathematician Pythagoras. They taught that the universe had a mathematical harmony whose secrets were written in a language that could be unraveled only by a chosen few. Mysticism, secrecy, and magic were the watchwords of much of this kind of thinking. The alchemists were its most notable practitioners. By a variety of random, magical processes, they sought to change one substance into another, usually gold. They helped to prepare the way for the science of chemistry. Belief in magic, in the curative power of herbs randomly selected, helped the great 16th century German physician Paracelsus and his followers to advance the practice of medicine. To the Paracelsans, both the cause and the cure of disease were to be found outside the human body. This was in contrast to the medical opinion of the time, founded on the teachings of Aristotle and the Greek physician Galen. According to them, disease resulted from an imbalance in the body's four humors or fluids. Only through bleeding the patient, purging him, or getting him to vomit or urinate could the imbalance be corrected and health restored. Not all of Aristotelian medicine was so primitive. In Italy, at the great Galenist medical school of Padua, the Aristotelian tradition remained experimental. Here, Andreas Vesalius, a young instructor of anatomy, began to copy the technique of Galen, whose works he was editing. Like Galen, Vesalius did his own dissecting while lecturing to his students. This contrasted sharply with what other anatomy teachers had been doing for hundreds of years, which was to read from one of Galen's texts while an assistant did the dissecting. Galen himself had to rely mainly on animals for dissecting purposes, since Greek custom forbade the dismemberment of the human body. Galen then related what he had discovered about animal anatomy to human beings. By Vesalius's time, the dissection of human bodies was less unacceptable to society. He was thus able to detect some of Galen's errors and to place the study of human anatomy on a modern basis. Modern physiology also arose out of this same tradition, for it was at Padua that its founder, the great English physician William Harvey received his medical training. Harvey rejected Galen's belief that the veins carried one kind of blood to and from the liver, and the arteries another kind to and from the heart. At first, Harvey agreed with Aristotle that the heart was the source of both kinds of blood. Later, after repeated experiments and observations, he concluded that there was only one kind of blood, that the arteries carried it away from the heart and the veins carried it back. Harvey's theory that blood circulated led immediately to such questions as, what does blood carry? And where and how does it pick it up? To answer these questions, scientists were prompted to study such functions as respiration and digestion. Sir Francis Bacon, Lord Chancellor of England under James I, urged scientists to abandon the haphazard experimentation of the alchemists, to leave the barren search for first causes, and to experiment systematically. Bacon argued that from this kind of experimentation, which he termed the inductive method, vast knowledge could be accumulated to build general scientific theories. Such arguments established Bacon's reputation in England. In the 1660s, Bacon's writings became very influential among members of the newly created Royal Society. William Gilbert, physician to England's Elizabeth I, was responsible for a theory that was to be of great importance to the future of science. The magnetic power of the lodestone to align itself with the pole star had been used by mariners in a primitive form of compass. Near certain coastlines, the compass needle deviated slightly, but constantly. This finding encouraged Gilbert to investigate the increased power of attraction present in larger land masses. From experiments with a lodestone shaped to represent the Earth, he deduced that the polar forces lay within the Earth itself. When Gilbert cut the lodestone in half, the pieces rushed together and held fast. This force, he deduced, held objects to the face of the earth, caused things to fall to the ground, and even held the earth together. Gilbert also deduced that this magnetic force was present in all other heavenly bodies and caused the bodies to keep their place in the universe. Meanwhile, Tycho Brahe, a Danish nobleman and astrologer, was compiling the first of the most spectacular achievements of the scientific revolution. To cast more accurate horoscopes for the Danish court, he made numerous observations of the heavens. He began with the great star of 1573, and his published description of it immediately made him Europe's most famous astronomer. Brahe devised several new instruments, which he housed in a splendid observatory. Brahe rejected Copernicus's theory of the universe. He contended that while some of the planets may go around the sun, these same planets, along with the sun and other planets, all orbit the Earth. Johannes Kepler, a Copernican and enthusiastic reader of Gilbert's work on magnetism, got himself taken on by Brahe as research assistant. Kepler needed Brahe's data to prove his own theory that the universe was constructed on mathematical principles which, to Kepler, were highly mystical. With Brahe's data, Kepler proved mathematically that planets travel in elliptical orbits, not in the circular ones of Aristotle, Ptolemy, and Copernicus. And with Gilbert's theory of magnetism, Kepler proved that there is an exact mathematical relation between the speed of a planet, its time of revolution, and its distance from the sun. The nearer the sun, the faster the planet moves. To Galileo Galilei, Kepler's theories, combining mathematics, mysticism, and magnetism, were as unacceptable as was Aristotelianism. Galileo had been brought up with an interest in mechanical things, such as Leonardo da Vinci's attempt in the 1400s to reproduce mechanically the natural flight of birds. Galileo also owed much to the recently discovered work of Archimedes, greatest of Greek mathematicians and inventors, one of whose water wheels is shown here. Galileo came to think of the universe as a huge machine, and of God as the master craftsman who had built it, set it in motion, and left it to operate on its own. With Archimedes' help, Galileo threw off Aristotelian ideas of space and motion and began to think in more abstract, more mathematical terms. By using an inclined plane with rolling balls, Galileo proved that Aristotle was wrong about the constant speed of a falling object, that a falling object actually picks up speed in direct proportion to the time it travels. Galileo extended this discovery to free-falling objects of unequal weight, deducing that they accelerate at identical rates of speed since they are subject to the same force. Galileo also deduced that a moving body will continue to fall forever unless some external force, such as the ground, stops it. Thus, he reasoned, a state of unending movement is as natural as Aristotle's state of absolute rest. With the telescope only recently invented, Galileo observed the moon and announced that it was not composed of Aristotelian quintessence, but of material much like that of the Earth. Galileo also used the telescope to observe the planet Jupiter. From a carefully maintained record of his observations, he discovered the 4 moons of Jupiter. If moons could orbit Jupiter, the planets could surely orbit the sun, just as Copernicus had claimed. Many other people were quick to agree. Galileo's opinions brought him into conflict with the Holy Office. This was the part of the Catholic Church charged with putting down all challenges to the orthodoxy of Aristotelianism as interpreted by Aquinas. But in the second half of the 17th century, Aristotelianism was to crumble before the onslaught of the new science. Galileo was the first truly modern practitioner. From careful observation and experimentation, including the use of precise mathematical measurements, Galileo gained exact knowledge through induction. He then tested this knowledge by using it to deduce new knowledge. Afterward, according to tradition, he tested these deductions at the Leaning Tower of Pisa. Galileo was able to see beyond the physical realities of the world, and by thinking in purely abstract mathematical terms, to form general concepts about the behavior of matter. Galileo was not fully modern. He remained convinced that Copernicus had been right about the circular motion of the heavens. In addition, Galileo could never imagine that an object moving into space might continue forever and never return to Earth. Nevertheless, it was Galileo who set the pattern for the development of science. During the next century, his methods were emulated by most scientists, the most significant of whom was the Englishman, Sir Isaac Newton. The scientific revolution was founded upon the recovery of Greek science by Western Europeans beginning in the 1100s, and upon their absorption and mastery of it during the next 300 years. Only then were scientists intellectually equipped to challenge its most cherished assumptions. Out of these attacks came a new science, with a new methodology, a new set of facts, and a new attitude toward the universe and everything in it. In place of a universe of purpose and first causes came one that was essentially mechanical, that saw the world as a device created, set in motion, and left to operate on its own. Galileo was the first scientist to follow this mechanistic approach consistently in his work. But during the century after Galileo, it spread to all branches of science and throughout educated society. How did this happen? What brought it about? How far-reaching was its impact on the rest of society? Mechanical tools of measurement were essential to the mechanistic approach. Modern mathematics began toward the end of the 16th century when François Viète regulated and reduced the number of symbols used in algebra. Within the 100 years following Viète, most of the still accepted mathematical symbols were either invented or brought into general use. During the same period, the Scotsman John Napier invented logarithms. Logarithms saved hours of labor, particularly in the elaborate calculations used in astronomy. By reducing complicated operations of multiplication and division to addition and subtraction, René Descartes, a French contemporary of Galileo's, developed analytical geometry, which proved to be of great importance to the study of the Earth's physical laws. Analytical geometry permitted scientists to state geometrical problems as algebraic equations and vice versa. It meant, for example, that a position on a surface, such as a location on a map, could be determined by a pair of numbers. The Englishman Sir Isaac Newton and the German Gottfried Leibniz, working independently of each other, were responsible for the most significant mathematical creation of the period. This was calculus. It made possible the mathematical investigation of continuous change by breaking motion down into a sequence of instants, much as does the motion picture. Along with the development of mathematics went the development of instruments for the new sciences. The compound microscope was among the earliest of these inventions. It enabled scientists to observe things invisible to the naked eye. The barometer was another early invention. It made possible the observation and measurement of air pressure. With the telescope, men could observe distant bodies of the heavens in detail. The thermometer permitted the measurement of variations in heat. The air pump, the study of the properties of air in a systematic way. And the pendulum clock, the measurement of small intervals of time. Mechanistic ideas spread through discussions in England's Royal Society and in other scientific societies all over Europe. Descartes' Discourse on Method, a charmingly written mixture of philosophy and autobiography, gained many converts to the new science. Descartes' own scientific method was largely deductive rather than experimental. The universe about which he wrote was quite abstract, like a giant blueprint transformed into whirlpools of matter. It was a universe that conflicted at almost every point with that of Aristotle, from Descartes' assertion that the lunar and sublunar worlds behaved according to the same laws because they consisted of the same matter, to his assertion that the human body was nothing more than a machine. It was the first time that a complete, non-Aristotelian scientific system had been produced. Another Frenchman, Blaise Pascal, set out to attack another of the most vulnerable theories of Aristotelian science, that air was weightless. Through a series of experiments with a glass tube, water, mercury, and red wine, Pascal discovered not only that each liquid has a different specific gravity, but also that a vacuum can be created. This experiment brought Pascal into conflict with the Catholic Church. In the 17th century, belief in the possibility of creating a vacuum or of finding one in nature was the same as confessing to atheism. In England, Robert Boyle was conducting other important experiments with air and with other gases, which were now being distinguished from air. On the basis of various experiments, Boyle came to reject Aristotle's theory of the 4 elements, and also the alchemist's belief that there were only 3. But an unsuccessful attempt to reduce glass to its elements by means of fire also led Boyle to doubt the entire idea of chemical elements and to stop short of laying a firm basis for the science of chemistry. This experiment and his own mechanist views persuaded Boyle that gold, for example, was built up of tiny bits of matter, which he termed corpuscles, and which could not be reduced further. During the late 1600s, Boyle was only one of several highly gifted scientists at work in England and on the continent. The most significant by far was Isaac Newton. In optics, Newton discovered that light behaves according to mechanical laws, and that white light is composed of rays of primary color. But Newton is best known for his work in mechanics. Here he drew on the work of Kepler, Galileo, Descartes, and others to construct a new scientific system. From observations, possibly including that of an apple falling, and experiments, particularly with a sling and a stone, Newton evolved a universal law that explained mathematically the attractive force that every particle of matter in the universe exerts over every other particle of matter. The Aristotelian distinction between astronomy and the physical laws of the earth was dissolved. Newton's universe was vastly more complex than any of the preceding ones. In Kepler's universe, it was the sun that held everything in position. In Newton's, it was the interaction of all bodies with one another. In England, Newton's ideas gained almost immediate acceptance from his fellow scientists. But on the continent, where Descartes' deductive mathematics dominated, their triumph took longer. Largely owing to the publicity given them by Voltaire, Newton's ideas eventually triumphed in France and spread to the rest of Europe. During the 18th century, scientists studied electricity and other phenomena by applying Newton's and Galileo's method of taking one characteristic, motion, shown by all bodies, and choosing other concepts, such as force, in whose terms motion could be discussed. The formulation of general laws for the behavior of these phenomena was, however, essentially the work of the 19th century. Newton's achievement, which seemed to explain the fundamental mechanism of the universe, speeded up the application of mechanistic methods to other disciplines. In France, Jean-Baptiste Colbert, one of Louis XIV's greatest ministers, gathered statistical data on the natural resources of France's provinces and the activities of the inhabitants. In England, Sir William Petty, a Fellow of the Royal Society, collected statistical information about the number of deaths in London caused by various diseases. John Locke used the new philosophy to launch a full-scale attack on the still fairly strong forces of Aristotelianism. Mathematics, not logic, argued Locke, was the only path to certainty. He contended that the rational methods of the new science should be applied to education and to government. Kings, he said, did not rule as a result of divine right, but because the majority agreed that it was to their benefit to let kings rule. If a king failed to safeguard the interests of his subjects, said Locke, it was reasonable and right for the people to remove him from authority. This was an idea that came to appeal to many of the North American subjects of George III of England, and afterward to the subjects of Louis XVI of France. In Holland, Baruch de Spinoza applied mechanistic ideas to biblical studies, arguing that miracles were impossible because nature follows a fixed and unmovable order. The new scientific ideas also produced some important economic changes. 17th century Holland was Europe's most prosperous country because of the close union of science, sea power, and trade. Holland was the home of the world's most advanced map makers, including the great Mercator, and it produced the world's most advanced scientific instruments, including telescopes, binoculars, and other optical devices. But in most of Europe, the economic benefits of the new science were limited to merchants and landowners. Most people did not benefit, since there was no large-scale alliance between science and technology until the end of the 18th century. In Britain, the Royal Society's long support of science to solve practical problems helped to bring about the Industrial Revolution. James Watt, for example, was able to design an improved steam engine partly as a result of his acquaintance with Joseph Black, a Glasgow scientist studying the nature of heat. John Smeaton, a member of the Royal Society, used his investigations into water power to improve the design of water wheels. He designed and built 2 water wheels for the Carron Iron Works, the first ironworks in Scotland. On the continent, where the emphasis had been on intellectual discovery, the tie of science to technology developed more slowly. But the range of discoveries in electricity, mathematics, magnetism, and astronomy was extraordinary. All this new knowledge and new way of looking at the world made little mark on the masses of Europeans. Their universe was still Earth-centered, and God's constant intervention was still thought of as natural. But the thinking of Europe's educated aristocracy and bourgeoisie was permeated by the mechanistic outlook of the new science. Their universe was a self-regulating mechanism without need of first causes or of God's intervention.